Our goal is to learn how to make a battery charger. We will make a model of a battery charger. The battery charger will consist of a bidirectional inverter which regulates the power flow between the DC bus and the AC grid. We will connect the battery to the DC bus and it will be charged or discharged. Then we will have a brief explanation of the already existing power electronic part of the model, which we have sent you via email. Then we will make the signal processing part, which will be used to control the inverter. Later, when we finish with the signal processing part, we will run our simulation using Hill SCADA panel. I will open the Typhoon Hill Control Center and existing model. As we can see, we have made power electronic part. Most of components we have already seen in the first and second session of Typhoon Virtual Hill tutorial, for example, resistor, inductance, current and voltage measurements. We even saw the three-phase inverter. So the only new components here are the battery, which is a model of a kind of a battery. When we double click on it, we will see that our model that we will use is a lead acid battery with a nominal voltage of 700 volts. The capacity is 120 ampere hours and the state of charge shows how charged the battery is, and it is 100%. Let's type, for example, 80%. And at the bottom we see a button which says Preview SOC Curve. When we open it, we will see our characteristics of our battery. Let's close this window. On the other side, a new component here is a grid simulator. Let's look under the mask. Grid simulator is a simple component made of the existing components from the Typhoon library. For example, this is a voltage source, the single-phase voltage source. We have two single-phase voltage sources more. We have the resistance of the grid and the inductance, and also voltage and current measurements. Go one step backward. When we double click on the grid simulator, we can set the resistance per phase and the inductance per phase. I have already set everything for our model. So let's start with the first element. The first element that we will use is a phase locked loop. It is the PLL component from our library. I will type PLL and take the three-phase PLL component. We will put it below the voltage measurement block and flip this component. So we will bring the voltage from phase A to A port, from phase B to B port, and from phase C to C port. We can move it slightly so that it looks better. This component has a few outputs. Only one output is needed for our control, so we will use only angle omega t. We will not use other outputs. We will take the probe component, connect it to the omega t output, and rename to omega t PLL. so it will be possible to observe during runtime. We will even use this angle for the other blocks in the signal processing part, so I will take a go-to block. We will connect it to the same path and change its name to omega t. When we have finished this, we need a transformation from the ABC reference frame to the DQ reference frame. We can simply type ABC in the library browser. From the signal processing category, extra subcategory, we can take the ABC to DQ component. We will flip this component and bring the signals from the current measurement components to the inputs of the ABC to DQ element. Phase A to A input, phase B to B input, and phase C to C input. As we can see, we need a reference angle, and this angle will be the angle from the PLL. Also, in our model, we will use the active and the reactive power information, so we have to measure it. We can take the power meter component and connect voltage measurements to voltage inputs and current measurements to current inputs. Now we have a few outputs. The outputs that we are interested in are PDC, QDC, and S outputs. It means active power, reactive power, and the apparent power. We would like to observe the signal with the Hill SCADA, so we will use the probe blocks. The first one will be connected to PDC, and its name will be P. The second will be connected to the reactive output, and its name will be Q. Third one will be S, apparent power. Now we can continue with our DQ part. Also, I forgot to mention that these outputs which are not used, we can terminate them with a terminator from the library browser. Let's just terminate one not used output. We can simply connect it to the D axis, for example. Now we will not have warning for D output in the message console during the compilation period. However, even if we don't terminate all not used outputs, that is not a problem for our simulation. Now we are going to make a PI controller here. We will use a sum block. I will flip it. I want first input to be plus and the second one to be minus. So we will double click on it and change the signals to plus and minus. After the sum block, we will insert the PI regulator. We will search for PID controller and put it on schematic. We will double click on it, choose PI for the controller type. We will type 0.015 for the proportional gain, and the integral gain can remain 1. We will open the PID Advanced tab and turn on the limiter. We want to limit the output of the PI controller between 1 and -1. We also want to enable anti-wind-up. Let's click OK. Now the icon of the component has changed. We can simply connect it to the sum block. We will copy the two connected components and paste them below. We will bring the D component to the minus input of the first block and the Q component to the minus input of the second block. For the plus inputs, we will use the SCADA input components, which will be the reference for D axis and Q axis. I will flip it and connect it to the sum block. I will change the name to IDREF, as in reference. Also, I will double click on it and change the default value to 10. The minimum value and the maximum value can stay the same. Let's apply the changes. We will do the same for Q axis. I can copy this one and paste it here. I will just reorganize this a little bit. We will change the name to IQREF. And also we will change the default value to 0. That is it. Now we will bring the output of the PI controller to the transformation DQ to ABC. We will type DQ. Flip this block and connect D to D and Q to Q. We will not use the 0 component input for the transformation DQ to ABC. Let's put constant component with the value 0. For omega t, we will use the omega t tag with the from component. This is it. Now at the output of the DQ to ABC block, we got reference values which will control the switches within the three-phase inverter. We can put these outputs into the vector with bus join component and bring them to the go-to tag modulator and later to the bus split. Here on this side, we will use a bus join component. Let's find it. We will flip this element and change the number of inputs by typing 3. We will connect them to A, B and C outputs. Now we will use a go-to block and name it modulator, the same as this one near the inverter. Now we have made the basic control, and here on this clean area we will make overcharge protection for our battery. We want to enable charging when the battery is not fully charged and to disable charging when the battery is charged. So let's start with a few elements. The first one will be comparator. we will need two comparators. The first one will compare the lower level of the battery with the measurement voltage, and the other one will compare the higher level of the battery, the full level, with the measured voltage. So here we need the constant value. The nominal battery voltage is 700 volts. For example, we will type that the battery is on a low level at 717 volts. We can change the name to low. We can copy this block and put it near other comparator and connect it to the inverting input. We will change the name to high. And the higher value will be, for example, 725 volts. To these two inputs, we will bring the measured voltage from DC side. I will reroute this path, so I will click on every corner that I want to break line. Now this path looks much nicer. Here, on the output of the comparators, we will insert SR flip-flop. The output of the first comparator will be connected to S input, and the output of the second comparator will be connected to R input. Now, if our battery is low, comparator 1 will be set and Q output will be logic 1 and the inverted Q will be logic 0. And with the comparator 2, we will reset the state so Q will be 0 and the inverted Q will be 1. So here we will need a few logical components. We will type logical and choose logical operator. We can drag it and drop it in front of the SR flip-flop. We need the AND logic. Also, we will copy this one and paste it below. We will need another AND logic with 3 inputs. I will copy one of them and paste it above and change the number of inputs to 3. Another thing that I would like to insert here is the SCADA input, which we will use to enable and disable this inverter, this control logic. We will take the SCADA input and change its name to enable. The signal type we can set to unsigned integer. The minimum value will be 0 and the maximum value will be 1. So I can connect it to the first input of AND block with 3 inputs. Also, I would like to use this signal for the other 2 AND components. I can simply connect it to this path. Now if the enable is 0, these blocks will not work because 0 will be present at the input. I will connect the Q output to AND component near and also the inverted Q to the AND block with 3 inputs. At the output of these two AND blocks, we will insert the OR operator. So we can duplicate one and change the operator to OR. When we have changed it, we can connect the AND outputs to OR inputs. Output of OR component will be used to enable and disable the inverter. So, we will use the GoTo block. We will change the name to enable. And also, we would like to observe the signal with digital probe. We will connect it to the path and change its name to PWM enable. Also, I will copy this probe near the AND logical operator with 3 inputs, and I will change its name to overvoltage. Now let's finish this logic here. To see if we have to discharge or to charge our battery, we will use the ID ref signal. From the library browser, we will take a sign component. We will flip this component and we will see how it works. If the signal is positive, the output of the sign will be 1. If the signal is negative, the output will be -1, and if the signal is 0 at the input, the output will be 0. Let's connect the ID ref signal to the input. That is it. And we do not need the -1 value, so we will use the limiter. From math operations, we will find limit. We are going to adjust this limit. The upper limit has to be 1. The lower limit will be 0. So we will cut off the negative number of the sign block. We will bring output of the limiter to the AND block and also to the AND block with 3 inputs. But before that, we have to invert this signal with the NOT component. We can simply duplicate any of the logical components and change the logic to NOT. We will bring the signal from sign component to NOT component input, and the output of NOT component has to be connected to AND component with 3 inputs. That is it. If we measure voltage on the battery is higher than the high limit, reset input will be set to logical 1, Q inverted will be 1, and we will send the signal to the AND block. Also, if the enable is 1, and if the ID is negative, we will charge the battery. Logic 1 will be present on the output and AND component with 3 inputs, so overvoltage indicator will be active. We have done with making control. We will click to save this model. And we will compile and open the model in HillSCADA. As I said, in the compilation log, we will see that the components' outputs are not connected in model, but this is not a problem for our compiler.